Hi there, welcome to the Linear Regression section of the SMLC course. My name is Arjun, one of the SMLC leaders, and I am very excited to teach you guys everything you need to know about the linear regression machine learning model. Now, before we begin with the content, I want to first give you guys a brief overview of the lecture videos that I'm going to be covering in this linear regression section of the course. The first video, the one you're watching right now, will be covering the theory behind the linear regression model. In this lecture, we're going to be understanding the ideas and applications behind the model and ensure that you have a good theoretical basis behind the algorithm. In the second video, we're going to learn more in depth about the mathematical underpinnings behind linear regression by covering the OLS method. A brief summary for it: OLS stands for ordinary least squares, and it's essentially the statistical method that helps produce the line of best fit that is so characteristic about linear regression. And we're going to be going over the specifics of it in the second lecture video. And finally, for the third and last lecture video, we're going to be going over the Python implementation for linear regression by utilizing a real house prices dataset offered by the scikit-learn machine learning library. So without further ado, let's get started with understanding the theory behind the linear regression machine learning algorithm. Now, before we actually go into exactly what linear regression is, I want to first introduce you to Francis Galton, the man who founded the idea of regression. So, a brief history. Galton closely studied the relationship between parents and their children, and in particular, he investigated the relationship between the heights of fathers and their sons. And of course, Galton discovered that the man's son tended to be roughly as tall as his father, as expected, but his breakthrough was that the son's height tended to actually be closer to the overall average height of the entire population, or of all people. And this trend was happening from generation to generation. And so Galton called this phenomenon regression, as in, a father's son's height tended to regress or drift towards the mean average height of the entire population. And to get a visual understanding of his findings, here we can see that this is the average parent's height, and we can see that as generations pass, the average height of the children is actually deviating or moving or regressing to the average mean height of the entire population. And this was happening from generation to generation. So now that we can understand that regression essentially means a deviation towards the average, let's kind of understand what linear regression is and how that ties into Galton's findings. So linear regression is a supervised learning model for regression tasks. And regression tasks essentially means predicting target values that are numerical or continuous in nature given a set of inputs or features. I know that sounds kind of confusing. I'll explain more about what inputs and features play in the scenario. But essentially, the idea of linear regression is that we're trying to predict target values or outputs or dependent variables that are numerical in nature. So some examples or applications of linear regression are predicting stock prices, predicting costs of tickets, predicting housing prices, predicting a company's profit estimation. All of these are examples of how all of these are regression tasks that involve predicting values that are numerical. And that's essentially the main usage for linear regression. So now that we understand the overall application and usage for linear regression, let's understand more about the goal of it. The idea of linear regression is to train a line of best fit on a set of training data points. So this here in this figure, we can see that these blue dots are all data points that we use to train our linear regression machine learning model. And an important idea to remember is that in order to develop a machine learning model, we have to feed it with training data. So with these data points, our model is going to learn and calculate a linear regression line. And when we're trying to calculate the algorithm is going to do this, or OLS, which I'm going to explain later on. But essentially, when we're calculating our linear regression line, we're trying to draw a line that is as close to every data point as possible so that we can reduce the loss. And what loss is, or residuals, is that vertical distance between data points and our line. So we're trying to minimize that vertical distance. In the next slide, I'm going to show you a better image to illustrate that point. But essentially, imagine a line between this data point here and our predicted value by our model. That vertical distance is called the residual or the error. And when we're trying to calculate this linear regression line, we're trying to minimize that distance as much as possible to optimize our model. And the method to do this, like I said before, is OLS, or ordinary least squares. And I'm going to be covering this more in detail in the next video, so stay tuned. But the main takeaway here is that this line of best fit is establishing a relationship between our dependent variables and our independent variables or features. And in this figure, we can kind of get a more closer look at what I mean by residuals and errors. Here we can see that this trained model is our line of best fit, or the linear regression line. And here's the observed value, or our training data. So essentially, we're using this training data to minimize the distance between our predicted value from our model and the observed value. And that distance is called the residual or error or loss, however you want to call it. The idea is we're trying to minimize it when we're training and calculating a regression line. And now I want to cover the two main types of linear regression. And this is going to be especially important when we're doing the Python implementation, to keep in mind what this entire idea of linear regression is. So the two types of linear regression are simple linear regression and multiple linear regression. Simple linear regression deals with one feature and a target, and multiple linear regression deals with n number of features and a target. So let's actually start from the basics. Let's understand what I mean by features and targets. So features are the independent variables or the attributes or factors and information that is not dependent on your target value or the dependent variable. And these independent variables or attributes or factors serve as the inputs that your model can take in to help make the prediction of your dependent variable. So essentially the idea is that the model is going to see correlations between these independent variables and your target variable that you're trying to predict. So let's think of an example here. Let's think of a linear regression model that's trying to predict the cost of ice cream. In this case, the cost of ice cream is going to be the target or the dependent variable, what we're trying to predict. And if our linear regression ice cream price prediction model is a type of simple linear regression, that means we're going to be only using one feature or independent variable to help train our model to make predictions on the cost of ice cream. And this one feature could, for example, be the weather. Because think about it, the hotter the weather, the more likely people want to buy ice cream in that time. So there's a correlation between weather and the price of ice cream. The model will be able to take in that information and data and realize that if the weather is really hot, if that's one of your features in your data set, then it can make a very reasonable prediction that the price of ice cream is also going to be very high as well, since more people will want to buy ice cream when it's hot, right? But if our linear regression ice cream price prediction model is a type of multiple linear regression, then we're not just going to be having one feature. We're going to have multiple n number of features and our target variable, which is the price of ice cream. So our set of features will not only be the weather, but it could also be the location, the competition, the population size, etc. All kinds of factors that have some kind of correlation to our dependent variable and prove to be useful information for our model when it's learning from the data and calculating that line of best fit. Also remember that this line of best fit is what's making the predictions. If I go back to this previous slide, what's essentially happening in linear regression is that this line of best fit is making the prediction. Let's say that we're taking an input of we're taking our input value and we're trying to predict the cost of ice cream. Let's say if the weather, or let's say if the temperature is 70 degrees, and let's say that's somewhere over here, then our model will predict that the price will be, let's say it's $10,000 here. When it's 70 degrees, it's going to make the prediction that the price of ice cream will be $10,000. So that's kind of the rudimentary idea behind linear regression. The line of best fit is what's making the prediction based on the inputs that is being provided. And here we can see this figure kind of gives a visual of that. Here we have a single predictor or feature, which is the independent variable. It's not dependent on the price of ice cream, for example. We can have our one single predictor or feature be, like I said, the weather or the temperature. And that's using that one feature, we're going to be making the predictions, right? But in multiple linear regression, we're going to have more than one feature that the model can learn from to make more high quality predictions. So generally speaking, when you're trying to, especially in Kaggle competitions, when you're given the data set, you want to make sure that your features actually have a good, strong correlation with your target with your target dependent variable, or else they're going to be useless and could actually ruin the accuracy of your model's predictions. So you always, and also it's a good rule of thumb to have more than one feature so that your model can understand the complexities within your data set. So those are some things to keep in mind of, especially when we move on to the implementation video. But that's pretty much it for the foundations behind linear regression. Good job. I hope this lecture proved to be useful in teaching you the basics of linear regression, and in the next video I'm going to be going through the explanation behind OLS, and we're going to be going more in depth about the statistical method and get a better mathematical sense behind the linear regression algorithm. Thank you, and I'll see you in the next video.